Okay, good morning everyone. Yes, so we have done mostly the continuous system as well. In the last class, we have seen that we have developed how we can able to. So, like if we see for the continuous lecture completely, means continuous structure lecture. So in that case, we can able to find it out. Like first, how we can able to write the governing differential equation, partial differential governing partial differential equation. Then from there, how we can able to proceed, how we can able to write the shape function which are frequency dependent in case of the continuous system, and we can able to find out what is the exact solution. We have also seen how we can able to do the model, like model responses from that, how we can able to do, how we can able to implement for a forced vibration and for free vibration, two cases separately how we can able to do. So up to that stage we have seen, and then we have also discussed that how we can able to formulate the transfer matrix which is connecting the left hand state vector of the left hand side to the state vector of the right hand side, and from there how we can able to establish the natural frequencies and all other things, how we can able to get that. So that we have actually seen clearly. Then the next phase comes, like okay, suppose if we are adding some lumped mass there, how we can again able to solve the natural frequencies for the systems. So these all the things we have checked in case of the continuous system. Okay, and here the way we solved that, we actually followed the principle of, like we solved the equation of motion as directly, like it is, we are solving it in the strong form. Okay, we did not go to the weak form formulation. We can also go for the weak form formulation, and we can also able to do that in the weak form formulation as well. So do you want me to show that one, like how we can go to the weak form and we can solve it? But I think that is mostly covered in the finite element course once you are studying that, because finite element is mostly to develop the weak forms from that and then they solve it. So if you wish, I can show it quickly, like okay, how we are formulating that, and then we can able to proceed. And we left two or things, that is like damping. We have not discussed about the damping, so that damping we have to complete it. Okay, okay, so let's see today, yes, how we can able to formulate that weak form and try to able to solve it. Okay, so let's assume the equation of motion for the bar. Okay, if we take that equation of motion for the bar, now how we can able to solve it? That procedure was very similar. Ux comma t will be equal to summation of j equal to 1 to n phi jx into qjt. That is always we will write it in that form. Now once we can able to write it in that form, then we can write del 2u del x2 will be nothing but summation of j equal to 1 to n phi j double dash x into qjt, and once we will have that will be j equal to 1 to n phi jx into q double dot jt. Okay, so if I just substitute that back to the main equation, maybe 1, what can I get? I will get EA into summation of j equal to 1 to n phi j double dash x into qjt plus rho a summation of j equal to 1 to n phi jx into q double dot jt, that will be equal to 0. That we can able to get. Okay, so once we will have this one, then what can we do? So first thing is that we can able to, means if we are assuming again that that is a harmonic type solution, so we can first like, or maybe we don't need to assume it harmonic solution. We have this way. Okay, fine. Now what we can do, we can first integrate it over the domain. So I'm just integrating it over the domain. So whatever is the domain, maybe length L, I'm just integrating it over that. Okay. If I integrate it over the domain, first of all, can I able to do that integration over the domain? And I'm saying that the differential equation is 0. Now, next step, I am just doing the integration over on top of it. First of all, can I able to do that? So if you think it practically, what is happening? You are saying that okay, in your each element is satisfying the equilibrium. So obviously the whole domain that is also satisfying the equilibrium. So that's why you are eligible to do that integration over the domain. Okay, makes sense. Good. So now if you do that integration over the domain, now how you are getting the terms? EA more or less is a constant term. Suppose you just take it out, then what will be there? Integral 0 to L summation of j equal to 1 to n phi j double dash x dx qjt. Can I write it like this way? Plus rho a 0 to L summation phi jx dx q double dot jt, that is equal to 0. Okay. Now if I write it this way, then I can also do the Galerkin approach here, because once I write it this way, then I can multiply with phi jx or maybe phi ix, that is some sort of I. Okay, and that is some other, not the jth, that is some other. Phi ix. Okay, can I write it like this one? Okay, if I can able to write it like this way, I can also able to write it like this. J equal to 1 to n phi I x into phi j double dash x dx into qjt plus rho a Okay, we can able to write it like that. Any doubt? Anybody? No doubt. Here, here we can think. So this becomes in the what form? this is the, you can say this is more or less we applied the weighted residual type formulation. Like you can see we are doing the integration and we multiplying with the weight factor. Like if I just think that this is the weight, like phi of x, phi j of x, phi j of a, these are the weights of that. So it is one type of weighted residual method we can say. Okay, so this is the Galerkin type approach in the weighted residual, that we are pre-multiplying with that same function or the same weights we are pre-multiplying. Okay, so by this way we can able to get it. And now if you think that once this thing is written, now our task is to solve it. So how can we solve that? This one is phi I, phi x, and this is the double dash. And here also another thing is very important. Phi ix and phi jx, they are orthogonal. So phi matrix should be choose in such a way that they are the set of the orthogonal vectors. We have also seen in case of the mode shapes, once we are calculating, all of our mode shapes are orthogonal with each other, so that if we perform any domain integration with multiplying both of them, or maybe the dot product of the two vectors, this should be equal to 0. So that property is always satisfying. So this will end up to 0 once, means that will end up to the Dirac delta basically. So once they are equal to 0, means once I and j are equal, they will give say 1, and if I and j are not equal, they will end up to 0. Okay, but what happened with this guy? Because you can say that phi I and phi j are orthogonal, but not, you cannot say that phi I and phi j double dash are orthogonal, because there is no guarantee that if the phi j it is orthogonal, then phi j double dash also it will become orthogonal. That nobody is giving any guarantee on that. Exactly. So that we cannot say or we cannot guarantee. So if I just think now from this point, if we are writing them in the matrix form, by the way, can you able to understand how can you able to go for the matrix form? What will be the coefficients? Okay, so let me just show you. So if I just go into the matrix form from here, we will have matrix like this way: phi1, q1t, q2t, q3t, like this way. Okay, plus rho a, q1 double dot t, q2 double dot t, q3 double dot t, like this. 0 or some forces may also comes into picture. Okay, agreed? Okay, so one thing, if there is some force, let's say if some forces are there, then once you are doing that integral, you have to also do it like this, and then once you are doing it here, you have to do it like that, you have to perform. Okay, don't forget that. If you have some forces, once you will be in that step, you are actually, sorry, not in that step, in this step, it will be like 0 to L phi ix fx dx, something like that it will happen. So don't forget that if you have force, your that force should be multiplied with the step function as well. Okay, so here either 0 or you will have like summation integral of 0 to L phi x fx dx, that will come. Okay, so now if you think here how these things will look like. So for example, first you put what is the value of I. So first you put I equal to 1. So I equal to 1 gives you the first row. I equal to 2 will gives you the second row. I equal to 3 will gives you the third row. Like this way it will go. Okay. So first row, if you do it here, 0 to L, phi 1, phi 1, double dash. Then 0 to L, phi 1, phi 2, double dash. Like this way it will go. And if you go down, suppose if we go here, phi 3, phi 1 double dash, like this way. Means I am just writing for the third one. So like this way we will get. Okay. Obviously that is with the dx and all those things need to be written. Okay. So this way that integrals are will be kept in the front of that. Okay. And here how will you get it? Here you see that you already acknowledge that if the mode shapes are generally orthogonal, so we will say that this full portion will be 0 and this full portion will also be 0. Just we will have only the diagonal terms, and diagonal terms will be phi 1, then phi 2, like this way. Means phi 1 square dx, phi 2 square dx, phi 3 square dx, like this way, with the integral obviously 0 to L. That way all the terms will be here. Now tell me, by looking at this equation, can you realize how it looks like? Or does that gives you some sense of what you have studied before? What? Sorry? Equation of motion of what? Not single degree. Multi-degree freedom system, exactly. So if you see now, this gives you the equation of motion of a multi-degree freedom system. Where these are the mass, exactly, and these are the stiffnesses. Get that? Get that point? So by this way, you see here, what is the beautiful point? Where it is not same to the previous method what we have done. Where is the difference? If you see, we have not assumed anything in the QT. We just left the QT as it is. You see, we have not touched the QT. We have not assumed whether it is harmonic, whether it is non-harmonic, nothing. We just say this is QT, this is Q double dot T. QT, Q double dot T is obvious, because once we are doing the variable separation, that is obvious that one will be QT and another will be Q double dot T. That is obvious. So we are just keeping like QT and Q double dot T, but we are not defining anything, or we are not saying that okay, whether the function is harmonic or not, whether the omega square will be coming, not, nothing. We are just formulating as it is. Okay. So this gives us a representation in the form like a multi-degree freedom system. And this also allows you another interesting point, that is you can able to choose your phi. Okay, so that's also another important point. And here additionally, your phi need not to be frequency dependent. Your phi need not to be frequency dependent, because here nobody is asking you to put the phi in terms of frequency. But you need to remember one point, that here the choice of phi is the most critical thing, because that is something what you are assuming, and that is the primary basis of finding your mass matrix and stiffness matrix. Okay, so to choose the phi, what can we able to use? Now here if you think, how many equations do we have once we are solving a beam problem, bar problem? How many equations do we have? No, not any question. How many primary governing differential equations we have? One is already written here as number 1. Then is there anything else? We have boundary conditions that I have not written here, but obviously we have the boundary conditions, and that boundary conditions you have to satisfy for calculating the phi x, because phi x you cannot take it, so means you cannot take it something which is not satisfying the boundary condition. You have to take phi x which will satisfy the boundary condition. Okay, otherwise that shape is not suitable for putting here, because then the end conditions will not be satisfied. Okay, So that condition you have to remember, that you have, like, once you are using it like this way, you have to first satisfy whatever the boundary conditions are there, and that will dictate what the value of phi it should be, means what should be the phi. Okay, got that? There sometimes some complexity can arise as well. That's not that sometimes simple. Maybe just I'll just show you. So like suppose now, as I mentioned, that it will lead to there. So if I think that we have a bar, one side is fixed and another side you are just giving some force to pull it, or some displacement maybe you have given and then let it go. So how will you write your boundary conditions? So you can write it, u of 0 comma t will be 0. Okay, and del u del x at x equal to L at time t, that will be also equal to 0. Yeah, that we can say. Yeah, and if you wish, you can give some sort of initial forces and not some initial force, that will be some initial displacement in that case. Or we can give some sort of like this way, that u L comma 0 will be 0. L comma 0 will be something, some value, maybe some displacement, maybe we are giving. Okay, so let's see how it will work. So that will be summation of j equal to 1 to n phi j 0 into qt, that will be 0. Okay, phi j 0 into qjt, that will be 0. So whatever the value of phi j 0 is coming, multiplied with qjt, that will be equal to 0. Now you can think qjt, that cannot, so if I try to express it in the matrix form, how can I write? So that is basically like this way, q1 q2 q3 whatever, and here phi 1 phi 2 phi 3, so that will gives you a 0. Okay, so what can I say from here? My basic point will be phi of j0 should be equal to 0. Simple point, because qj cannot be 0 and all the terms are there, they can be plus minus, so many things. So the best solution of that is that this one, that phi j of 0 should be equal to 0. So whatever the shape functions you are taking, okay, whatever the shape functions you are taking, doesn't matter, it should be 0 at x equal to 0. Okay, so for example, if you see that previous case, once we have solved, so it is a second order differential equation. So phi x has a order how much? 2. Second order differential equation. So we can say that if I assume that solution of phi jx is like a1 e to the power of lambda 1x plus a2 e to the power of lambda 2x, that way we can assume, or we can assume a1 cos lambda 1x, it's cos lambda x only, not lambda 1, cos lambda x plus a2 sin lambda x. That two way we can assume. Okay, the last one will be easier, because in that case what will happening, you are saying that phi, or maybe a j2 this way, so you can saying that phi j of 0, that will be nothing but aj cos 0 is 1 plus, that is equal to a1j, that is equal to 0. So you can say that your function is becoming a2j sin lambda x. That will be becoming your function. Or sorry, that will be lambda j. So that lambda will also be changing. Yes, so lambda j. So you can say that all of your how to say that the shape functions will be some different a of the lambdas, means the lambda x, means the sine lambda x, then sine maybe 2 lambda x, 3 lambda x, like this way it will come actually. Got that point? And why it is sine? If you are putting it sine, then you see, if you put x equal to 0, it will eventually become 0. There is no doubt. So your first boundary condition is always satisfying. You cannot put cos here, because if you put cos, it will never be 0. And you can also be able to understand that if somebody tells that, okay, it is just like 1 or something, then you should put cos, not sine. Make sense? Good. So this we get 1 point. Nice. Now the next thing comes that, okay, you will have del u del x at x equal to L. So if we are just assuming this one, because it is a second order differential equation, so we can assume this way, that form. And then now if you are substituting it here, then it will be phi dash jx. So we will get it 2j lambda j cos lambda jx. Now you please substitute x equal to L. So now at x equal to L, what will be the value? A j2 this cos lambda j into L. It will be equal to 0. Okay. Now you see, very simple point. This can be 0. A2j into lambda j, can they be 0? No. So the option remained cos of lambda jl should be equal to 0. Okay. So cos of lambda jl is equal to 0. That means lambda jl, what is the solution? General solution, please try to recall. 2n plus 1 into pi by 2. So what should be your phi? So phi of x should be your some constant number. Maybe I should not put a actually, maybe I should put it b, because a is the area, but don't get confused with that. Okay, so b into sine of lambda. So okay, so lambda is equal to, so lambda j should be equal to 2 by 1 into pi by 2 L. Okay, so I can just say this will be nothing but 2n plus 1 into pi divided by 2L into x. So that will be my shape functions. Or maybe I just put it j. Yeah, so that is phi j. So for the first one, once you are calculating, I can also write it minus here. That is also equally okay. 2j minus 1 divided by 12, 12, that is also fine, not a problem. So if I just put for first case j equal to 1, I will get, so let's say what are the functions we are getting? b1 into sine, then here it will be 2 into 1 is 2 minus 1, 1 pi by 2 into x by L. That will be your first solution. What will be your second mode? Second mode will be b2 into sine, how much? Pi by, that will be 2 into 2 minus 1, that is 3. Make sense? Make sense? So these conditions always will satisfy your boundary conditions. And additionally, if you see, they are orthogonal with each other. So that satisfied all of the things. And you can easily able to put it there and able to solve that. Make sense? Did you get that point? That how you should calculate the phi. Now here, if you try to recall, where is the difference with the finite element? Shape function, exactly. In finite element, we are not calculating the shape function from the boundary conditions. We just pre-assume the shape functions, that this is a linearly variation. Therefore, you should understand that once you are solving a cantilever beam, your shape function for that, and once you are solving a simply supported beam or like this bar, they all will be different. Whereas in case of finite element, they all are same. So your life in case of finite element is much easier. You just have an element, you just put it, done. You are not at all thinking anything behind that, what should be the better way to approximating it. You are just using it. But once you are coming to the spectral or some sort of like a mixed type of method, there you are trying to designing that, okay, this should be my function, this should be the function of that particular boundary condition, so that my solutions can come much easier. Okay, so here is the difference actually with the finite element. And due to that beauty of the finite element, that you can say it is does not matter of the boundary condition, it doesn't depend on the boundary condition, that how the boundary conditions are, therefore it becomes general. You don't need to at all think that what boundary conditions you are using. Like for example, you make some structure, then next day your client told no, you should not do it with the fixed, you should do it with the free and fixed. Then again you forget that, okay, to change the element and all those things, you run it and your full result becomes something nonsense. That you don't need to think, because there the element does not depend on the boundary conditions, that is free from the boundary conditions. Okay, but here element is dependent on the boundary condition, and therefore also your solution are much more rigorous and much better, because there you are solving a general thing, and here you are tailor-made for every particular problem. Like for example, you purchase a shirt from the market which are like ready-made shirts, or you make your shirt from the tailor. So obviously there will be a difference in the fittings. So that exact thing you can think that coming in that two method. One is the tailor-made for particular problems, and another is the general that can be used for all the places. I think you get that ideology, that where are the two things different. Okay, got that? And this method you can see we can do it in any stage. I hope you get that point. First stage, if we are like just going back, that was my solution, means that was my equation of motion in the equation 1. You can even start solving it in that stage, absolute strong form. You can even do it. That will gives you the spectral element type matrix. There your shape function will be frequency dependent. Okay, now next step, if you do the weighted residual type integrations, if you perform, and if you then implement the shape functions calculated from the boundary conditions, and if you put it, that will also gives you the solution. Okay, and third case, which is the finite element, actually there you have to do it again integration by parts, because there you will not allow to do like this type of integration where you are having one with phi x and another with phi double dash x. You have to make both the thing equal. So you will perform one time the integration by parts, so that you can reduce the order of the one and increase the order of another and make them equal, and you will perform that. So that will become your finite element. So these are the three stages of refinement you can call, and three stages are giving you the three types of solutions, and all are useful, all can be implemented if you know what are their limitations, where they are actually using, and I tried to just cover up that full stories here. I hope is that very clear to all of you. Any doubt, by the way? Clear? I think this is nothing but like we are just solving it at the different stages. That's all. Yes, don't say anything. Okay. Good. Good. So we can able to get it there. Nice. Now you can also able to realize one interesting point that also I should also mention, that if your excitation is not purely harmonic, like suppose for example you are solving for some response, like you have some time response, then I think you can understood that first method where we are making the spectral element, or directly like we are assuming the harmonic solutions and we are making the shape functions frequency dependent, I think that you can realize that is not that suitable, because once you are solving something you maybe not want a frequency dependent shape functions, because here you see it is, you can put it any type of time space, you can give qt, you can take what is the q double dot t also, and you can able to solve it as like a normal structural dynamics problem. Like this can be solved like you can use the Newmark beta or Runge-Kutta, ODE, all can be used here, because you will get a definite shape function, definite stiffness matrix and definite mass matrix, so you can able to solve that in like a normal methods what we have discussed in the numerical analysis, you can able to solve it. But there in the spectral element case you will not reach up to that stage. There what you have to do, you have to take the excitation, you have to go for the Fourier transform, so that you will get what are the frequencies contains in the Fourier domain or in the frequency ranges. You have to calculate the responses for each frequencies, you have to multiply both of them and you will get the solution. Then you have to do the inverse Fourier transform to get whatever is the time history is coming, and that has a limitation that will be only limited for the linear system, not for the nonlinear system, because your model superposition will not be valid for the nonlinear systems. Here also that limitation still remained, that is it is valid for the linear system. Can you tell me where I have used the model superposition? Here. By the way, here did I use the model superposition first of all or not? Sorry? Exactly. Summation of phi jx dx. So that is the model superposition. Like you are actually summing up all the modes and you are getting the solution. And you see, we are not at all disintegrating it. And that's why we get that matrix. Because this is that nothing but the summation form, which is written in the matrix like this way. So there is the model superposition. Okay. Make sense? Good. We can get that way. Yeah. So I think we got a decent understanding on like how the things are actually happening. Okay, we have not done one thing. Here, if you see, we have not solved this thing. Let's complete it so that we will can able to say that full thing. Okay. So we get the shape functions. So now once we get the shape function, so we can see what we have EA into that full thing with Q1T, Q2T like this plus rho E into a diagonal matrix with Q1 double dot T, Q2 double dot T like this, equal to zeros or whatever. Perfect. So this matrix we can able to get, this we can able to get. Agreed? Once we calculated this phi, we can able to get that, because this is nothing. It is just like integral phi 1, phi 2, phi 1 like this, that I and j with dx 0 to L. So that can be calculated. So this full matrix can be calculated. This full matrix can also be calculated. Okay, any doubt? No doubt. What we are looking for in this solution? Sorry? Q means, or maybe more specifically, Q1, Q2, Q3, Q4 we are looking for. Okay, and this is a set of so that has like n number of modes if we are considering. So then it will become n cross 1. This will also become n cross 1 if we are considering the n number of modes, because that number of mode can be anything. Okay, because then it will be just like increasing that b, and we will just start getting that. So we are not restricting ourselves, we can take it in. Whatever the value of n, you can put it and we will get that. Nice. And here, among these three, these two have already been used, that first two. So first two, if you see, they are basically boundary conditions. But what about the third one? Please somebody told. Initial condition, exactly. That is the initial condition. So if you see, boundary condition gives us what? They gives us to tuning the phi. Okay. So initial condition should gives us what? Q. Exactly. So you have already seen that in that problem, now we dealt with the phi. We do not have any problem with the phi. Phi's are sorted fully. Okay. But we still remain to sort the Q. Agreed? All of you? So obviously that's why the initial conditions are not used yet. Now we have to use those initial conditions. So this is one of the initial condition. Okay. Any other initial condition can be possible. Now just try to recall the single degree freedom system. Yes, please. Velocity, exactly. So we have one term from the displacement and another term we should have from the velocity. So let's write the velocity one. This will be 0. Okay. Now the question is, should I write only these two, or should I need to write something more? Let me explain my question, rephrase my question. If you see, in boundary condition, please pay attention. That is u0 comma t. That means what? If I try to draw it, that this is your t and this is your x, or maybe opposite way, doesn't matter. So in case of boundary conditions, once you are defining it, you are defining 0 comma t, means at x equal to 0, complete value of t you are taking. So that means it is a line in that. Agreed? X equal to 0 and t, all the values you are taking. Next one is x equal to L and all the values of t. So that means x equal to L and all the values of t. So these are your boundary conditions. But now if you try to plot initial condition, how does it look like?
First one,
X-axis, but will that be a full x-axis or will that be a point?
what?
It's a point, exactly. It's a point. So if you see now, it become a particular point that, yes, so it is a point x equal to L comma 0. Now my question is that, will that be okay, or should we need some line here also? Now maybe I can try to rephrase my question again, that how can we able to perceive that point? For example, if you think we are having a system, fine. Now if we are saying that okay, the end point is how much displacing. So here what we are specifying, that is just end point, how much it is displaced at t equal to 0, at the initial time how much is the displacement. But we have not told how the internal thing is expanded, because it cannot be just that discrete point get extended. That cannot be possible. Once we are giving some sort of like extension, that will full bar will be extended. It is not that a single point is getting extended and other points are remain same. That's not possible. Exactly. All of you agree with my point? So if we just give that boundary condition, then we are silent about how the other points of the bar is extending. We are not giving anything. We are not saying that they are equal to 0. That means there is no displacement. Rather, we are silent. We are not saying anything. Okay? And other hand, we are saying that okay, that velocity is also 0. That is okay. But similar type of matter, like displacement, and the other point is the velocity. Okay. So now let's try to see, is that a sufficient or they are not sufficient. So do we need to describe the full field, how it was at initial stage, or it is not required. Now I can understand, obviously it will be very difficult for you to initially predict how its shape should be. But let's see whether it is required or it is not required. Okay. So let's see. So we have this equation, that is u of L comma 0. That means u of L comma 0. That is what we can say. Again, similar manner, phi 1, phi 2, phi 3, phi 4, like all those with q1, q2, q3. So here we can put 0, 0, 0, 0 with a 0. Okay. Now, please check. If I say that exactly we are discussing, that what it is, initial condition or boundary condition? Initial condition and the boundary. That is that way we can say, because in the previous two they are clearly boundary condition, no doubt, because that is varying with the time, as I have drawn that is extended over the time. But here it is a point, so it can be initial condition, it can be boundary condition as well. So let's see. And my another question was that should we need to give that full variation at t equal to 0? Exactly. Instead of L, should it be X? Full shape we can able to get. So what is required? Means, is it sufficient enough or it is not sufficient? That we have to see. So you can see that is not 0, that is u actually. So that is some value of u is coming here, and here once we are putting it, so that will become like this way. Now the question is, once this way it is coming, that phi 1L, phi 2L, phi 3L, phi 4L, and Q things are coming. So these will give you a particular value, because now phi is known to us. Phi is known to us. So this will gives us some value. Okay. So can we able to solve that? Because we know once we start this solution, we need the initial condition. Initial condition should be known to us. It is not that initial condition is not known and we can able to solve it. No.
All initial condition for all.
Exactly. Initial condition for all the step functions. That is required. Otherwise, you cannot solve it. You got that point? Means, where is the problem happened? Now this is n cross Now this is 1 cross n, this is n cross 1, and this is 1 cross 1. So now you have n number of unknowns, and you have to solve it from a single equation. How it can be possible? It is not possible. So you cannot able to solve it. So how? What is the way? It is also difficult to know the full shape, that how it is varying. So what else we can able to do? Let's see what else we can do. So what we have? We have u of L comma 0, that will be equal to u. Okay, and we know u of x comma t, that is equal to phi phi jx into qjt. And once we are writing it, it is coming like this way: phi 1 x, phi 1 L, phi 2 L, phi 3 L, phi 4 L, dot dot dot, with equal to q1 t, q2 q1 0, q2 0, like this way, with a 0. Okay, agreed? Now if I do some craziness and write it, so once this type of things are happened, how should we have to do that? We have a very nice way of doing the weighted residue. So again we can do that. So phi I of x, I am pre-multiplying it. Okay, but that will be again a problem. I show you. Just a minute. Okay, can we perform the integral? We cannot able to perform the integral because that portion will not be integrable properly. So to encounter that, can I write it? That's a Dirac function. So at a particular point of L equal to x, that will be 1, and all other point that will be 0. So if we do that way, then we can able to rewrite that. And then we can able to again do the full integrations. Now the good point is where you can able to put phi 1, phi 2, phi 3, phi 4, all the things will be coming, and you can able to solve it. So how many number of phi is there? That many number of I you will go, and it will be having that type of matrices, this, and then you can able to solve it. And here it will be not 0, it will be u, and that type of things will come in here. Continuous is really difficult. It's not that easy stuff, and it really need like so much mathematics involved into it. Or else the another simplest solution, multiply with the phi, whatever the shape you know, that you know that okay, this much of u you have, so you know that how the variation is happening, that is with the sine of omega t, I mean sine of lambda x, multiply with it so that you will get the same. That way also can be possible. So by this way you can say that okay, q1, q2, q3, q4 all will come, you can get it. Because most of the cases continuous, none of these, you will not get any lecture of this type of thing in the so detailed manner that okay, these are how we implement these, how we implement that. how these methods are coming. Maybe if you also read the book, it will be not that way clear because they will give it in the different chapters. And the chapters are not that way interlinked. So once you do it by yourself, then only slowly you will realize it that okay, they are this way that the things are coming. Okay. Good. So do you want me to show also the how finite element came? So we went up to that stage. Maybe I can just draw, write one more steps, and then the finite element can be derived as well. So I think up to this stage it is clear cut. And once it is zero, like if you see the next one at this as it is like that one is zero. That is very simple. That everything will be zero, not a problem. But once they have some value, then it's get the problem. Some value means how they are arranged to have that value. That knowledge is the difficult thing. That how they are arranged. What are the weights of each of them so that it will become that much. That's a peculiarity. You can correlate it with some sort of way in case of the multi-degree freedom system.
Force vibration is fine.
Exactly. That 5 into F we doing exactly. So that type of similar scenario is here. Means you have to think that how that displacement is divided. Means they are following the sine shape. You mostly know that. So you can actually think that okay, this is the sine shape. Now sine shape, how other things are modes are come. But you need to remember they are modes, not nodes. Node you can see, okay, these are like 5 nodes that they are equally divided. But modes you cannot say they are equally divided 5 modes. No. So that you have to really feel it intuitively that okay, how they are coming and all those things. Okay. So that's why if you remember I mentioned once I was teaching that eigenvalue. That is the skeleton of the full structural dynamics course. If you really understood the eigenvalues and eigenvectors properly, you are more or less in a good shape. You can able to grasp it fully. That is very important because everywhere that is act as a fundamental, and then all the things are developed on that on top of it. Okay, so we go up to that stage. Yeah, we understood. Now, if you see in case of the finite element, how we go? We have so finite element. This force up to this stage we go. Then what we do? Here we start playing. Here we do a integration by parts. Okay, integration by parts means you will remember.
This 5K double that it's to 5 days.
5 dash and 5 to 5 dash. Yes, exactly. So we'll get that. So if I just quickly do it, EA integral summation summation j equal to 1 to n integral 0 to L phi I x phi j double dash x dx. Anything else? No, QJT. I'm just taking the first term. Other term you don't need to take. That is remains same. Okay. So if I take this term and integration by parts means we are doing uv dx. Anybody remember the formula? Actually, it is not required. I tell you how. You can write it ddx of uv. That all of you know how it is. Plus that we mostly know, everyone. No problem. Very good. Rearrange it. Okay, now integrate it. Okay, see what it comes. That formula. Okay, so like I can't remember that, so I generally do it like this way so that it will be done. Okay, so now if you go back and try to check, or you can also rewrite it in that form or this form. Both the forms are okay. Means from here we can write another way, that is v into du dx into dx, that is exactly similar to this. So this is my v, this is my du dx. Yes, this is my du dx and this is dx. Okay, so that will be uv minus integral of u dv dx into dx. So if I just write it, EA summation of j equal to 1 to n integral of 0 to L. Yes, so u is, this is my du dx, d2u dx2. Oh, no, not d2u dx2. Means this is some sort of du dx. Yes, okay. This is du dx. This is my v, and this is this. So v into du dx. So u into v, and then minus. So first, like, okay, just let me do it. U into v. U means here how much? So that will be v is phi 1x, and this one will be phi dash x minus 0 to L. You will have u. U is u into dv dx. So phi I dash x into phi j dash x dx with qjt. Make sense? Now, sorry. And this full thing will be under like this. Now the point is where that this part can be come from. Please come on, you have done the finite element. Come on. This came from boundary conditions. Simple. So boundary condition will be substituted here, because that will be like once you have completed the integration, so it will be 0 to L. So you have to substitute the values of 0 and substitute the value of L. So that way we can able to write it EA, then we will have summation of phi I L into phi j dash L minus summation of phi I 0 into phi j dash 0 minus integral 0 to L phi I dash x phi j dash x dx into qjt. Now if you see that full thing, like phi I L into phi j dash L. Now if you think here, what will happen? Phi j dash L. Phi j dash L will be 0. Phi j dash L will be 0. Because that the strain at L will be 0. So phi j dash L is equal to 0 and phi dash 0 is 0. So that full thing gone. That will not be staying there. That vanished. So you are left with this. So this way you can say that finite element comes into picture. And the good point is where you see that you don't need to put the 515 calculated before. They are already substituted here in your equation. You got that point? So now if you can satisfy this equation, then it will be satisfying the boundary and all those things as well. And if something is present in your boundary, that can also be taken care by this, because that term will be there. If they are not zero, there that value or that quantity will be remained. Got that point? So this way the finite element actually works. So there actually the boundary effect of boundary condition is actually went inside the weak form solution. And so I hope like you get the idea of that three methods very clearly, that how they are different, how they are coming. And also here the matrix will be little bit different, because in the previous case if you see, your matrix was, the stiffness matrix was phi I into j dash, j double dash. Means in the second case your stiffness matrix was integral phi I into j double dash, but here the stiffness matrix of the finite element is this. So that is different. And if you see in spectral element, you cannot distinguish the two matrices. Your stiffness matrix and mass matrix is fused. So there is like a, and all more or less gives the same result, but you can see they are in the very different forms. Okay. I think you got a quite clear idea on how the methods are working. And with this, maybe we will conclude here today's class as well as also the continuous system, because I think continuous system is like a also like a ocean. So we don't need to go further. We just need to close it here. Okay. Because this is itself already too deep.